Yeah, it's 4:10, so I guess let's start. Uh, so, so we just thought to have this informal kind of paper discussion groups where we talk about just computer vision stuff. Mainly because we weren't excited about computer vision, so we thought maybe we can have this group where we talk about computer vision. So that was the idea behind starting the special interest group, and there's there's a lot of pressure right now on computer vision researchers. My last few days were doing this. I was waiting for ICCV rejection, and then I tweeted about it, and then I actually got an ICCV rejection. Uh, but but I guess there's always another con. So just had to remember for all researchers, triple AI is in 20 days. So just thought to have something informal to cool everyone down until triple AI or 3DV if you are submitting to that. Uh,
So yeah, this event is sponsored by GitHub, and make sure to scan the QR code for all the student benefits of GitHub, such as Student Developer Pack, for Copilot, and Canva Pro. And also feel free to grab some pizza and some GitHub stickers if you want. Enjoy our event.
so I guess like one of the things was we should have brought more pizza, and I realized that right now because so we had the registration form and two people filled that out. So we thought according to two people, one pizza sounds good. The first event was different where more people filled it out and we got and I guess we got three pizzas. So yeah, just like fill it out gives us an idea of how many pizzas to get. Wait, sorry. Oh yeah. So I mean it's completely optional if you want to. No problem. So so what we thought to do is have like not a paper reading but a paper discussion where feel free to stop me at any time. I'm not presenting the paper. It's just like a discussion. And we thought that since CVPR was almost there, I guess all of us might be reading CVPR papers right now. And so we just thought maybe let's go through CVPR papers and let's discuss CVPR papers first. So yeah, we'll be discussing CVPR papers in this group just because kind of everyone's reading those right now. Uh, yeah. So the paper today we picked up, and we'll also like decide the next papers. But the paper we picked up today was distillation of guided diffusion models. Uh, the at least when I first read this, to me it seemed like a pretty heavy paper. There's also so what I usually do is I just read figures and yeah, that's pretty much how what I do. And the only figure they have over here is, I guess, deterministic and stochastic sampling, which is not really a contribution of this paper. So it's a bit dense, but maybe we can still do discussion of some kind. Yeah. So distillation of guided diffusion models. I guess like all the words are not something new for most people here. There is also oh 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 yeah. So for sure, yeah. So 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 diffusion is just like a pretty recent method. Actually, not so recent if you think about normalizing flows and uh, MCMC and all that before that. Kind of just directly leads to diffusion, especially normalizing flows. But so the main idea with diffusion is you have some you have some pure noise and then you do some kind of noising step on it. The most common one is you just add Gaussian noise in it, and then you train a unit to recover that Gaussian noise. This is like a very high level introduction with uh, kind of what diffusion models in general do. So this is also like a fully diffusion, a fully con diffusion model and all that. A lot of variations right now, but the main idea is just if you can try to denoise images in such a way, and turns out that if you try to do this with pure noise, and you can actually generate pretty nice images. So you have like an image, you add some noise to it, then the diffusion model denoises it, and you end up generating pretty nice images. Uh, uh yeah, it's also pretty uh, pretty much related to the kind of stuff, the motivation behind GANs, which is can we turn pure noise into some new image. So I was just seeing the authors of this. There's of course Jonathan, who was the first author of DDPMs. But what I like to do, I guess, is and feel free to tell me if you want to do it any way different. But I like to go through images first, and I guess maybe you can go through this image then. So so what this says is distilled stable diffusion samples generated by our method. So distilled stable diffusion is not something new. There was, I guess, already this paper that was about progressive distillation or fast. Yeah, there was this paper which is also by the same authors, and that already distilled stable diffusion. So I guess this is not something new, distilled stable diffusion. But then they say generated by our method. Okay, so these are the ones, and they have some two-stage distillation approach. And oh yeah, yeah. So and I guess this could be the main contribution, which they say only 1 to 4 denoising steps on various tasks. Yeah. So if we see the images, and these are compared to standard classifier free diffusion guidance, we reduce the total number of sampling steps by 20x. Okay. So these images actually look pretty good to me. Just seems like something out of classifier free diffusion guidance, but they do this with just 1 to 4 denoising steps, which I guess is really interesting because normal diffusion models take at least stable diffusion was 500 and something steps, 500 and something denoising steps, and other models are getting larger and larger. So, so I guess that's a nice thing to reduce the number of denoising steps. Probably also reduces the complexity. Okay, but I guess that's the first image we have over here. And probably a nice next step for the discussion would be reading over the abstract together. Uh, yeah, maybe let's go over the abstract together. And oh, first off, I don't like this formatting. I don't know if you agree with me, but if you have a 3/4 page image, you should never have two text over here. Okay, okay. That's just me being picky. I guess the reviewers did tell them this in CVPR, probably. Wait. Okay. So they say classifier free guided diffusion models have recently been shown to be highly effective at high resolution image generation. Yeah, that seems about right. And they have been used in large scale diffusion. However, large scale diffusion pose an approach to distilling classifier free guided diffusion models that are fast to sample from. So I guess this is their main contribution, fast sampling methods. And then they say, given a pre-trained classifier free guided model, we learn a single model to match the outputs of the combined conditional and unconditional model. And that requires fewer sampling steps. And apparently they work on this for the pixel space. And do they, oh yeah, they also have Lion, which would, I guess, be on the latent space, but do this, yeah. They also say that they are able to make it work for latent space as well. Interesting. That that sounds nice. And I guess this also makes sense because um, this is just, I guess, like all of this is just describing what distillation means, which is rather common. So nothing new over there, but it will be interesting to see how they do this for diffusion. Yeah. And then there's the introduction, which I guess we could skip right past, but they have an image. So probably let's go over the image. Okay. Uh, so in this they say class conditional samples from their method. Okay, okay. So I guess this is from their method. So probably we should take a look at this later because we haven't really got into seeing what they propose. We just know that this is some kind of diffusion.
Mentioning the aspect of this model takes like 4 what do others like?
Yeah. So I guess you might know stable diffusion for sure, and stable diffusion takes 500 something steps. I'll need to verify for the exact number, but there's also uh there's also so classifier free diffusion guidance was also trained on a lot of steps. When so there is Yeah. So this model also also got SOTA on a various number of tasks and was supposed to be one of the top models. And this was also trained on, I guess, 1,000 steps. They had a variant of this trained on 1,000 steps. So that so yeah, they bring that down to 2 to 4 denoising steps. But I mean, the other thing with distilled models is you cannot really compare steps. So even if you I guess think of connates and you try to think of distilled connates and like think of one forward pass through a distilled connate or one forward pass through just a connate. You cannot really compare them. So I guess the exact number doesn't make a lot of sense, but it being so low does make some sense. Uh, oh yeah, yeah. Oh yeah, the computational complexity definitely decreases drastically, but what I was also saying is, uh, so let's say you try to do it in let's say you do it in 3 steps, and then you have a pure diffusion model uh, that does it in what 9 steps. Then this is not supposed to be 3 times computationally less complex because yeah, but yeah, that makes sense. This would definitely be a lot more easier to sample from. Yeah. Then they give some background on diffusion models. I guess this is rather simple. We just have the very standard expectation. I guess this should be parameters theta. Uh, yeah, because it's and we have the denoising model. We compare it with the original model. So yeah, this is actually the pretty similar loss. And yeah, this is just a standard DDPM reconstruction loss. There's of course the signal to noise ratio, which they changed, and there's also the W term, which means how much it's reliant on guidance. Uh, so I guess they also adopt that approach. So not just standard DDPMs, pro- but they but this is like pretty self-explanatory from other papers on DDPMs and diffusion guidance and DDIMs. So they give some background on DDPMs and DDIMs, which I guess we can skip right past because they are very well known out there. And they also have the DDIM standard sampler. Uh, yeah, this also makes sense. Uh, and then they give some. I guess this is an interesting part to read because this is directly related to their paper, uh, progressive distillation, and and I guess what they say over here is their approach is inspired by progressive distillation. So progressive distillation would be, I guess, yeah, it's this paper, which was the only one earlier on progressive distillation for diffusion models at least. Okay, so their approach is inspired by progressive distillation, and that's an effective method for improving sampling speed of unguided diffusion models by repeated distillation. And this could not be applied to distilling classifier-free guided models, uh, or studied for samplers other than deterministic DDIM samplers. So, so their main contribution seems to be to resolve this and make it work for guided diffusion as well. Yeah, that seems nice. And I guess like one of the main things is just at least like one of the main things for progressive distillation. This paper, this was last year, Eichler. That's nice. But I think like one of the main things or assumptions for this paper is uh you're not really considering if the weights of some classifier could be injected, or or even if you could directly use classifier guided diffusion, uh, and they don't and they make a lot of assumptions which don't really account for this. uh, this is also an interesting paper to read through, but they make a lot of assumptions which don't really allow them to move past the unguided way, though even if it's like classifier free or or just standard guided diffusion. uh Here their assumptions, I guess, limits them, so would be interesting to see what they do over here. And then they have this background on latent diffusion models, which I guess is also uh, pretty straightforward because of stable diffusion and just how popular stable diffusion is. So yeah, so at least over here, what they mean by progressive distillation is, um, is your so what they do in this paper, the 33 one. So what they do in this paper is they try to take a trained diffusion model, treat that as a teacher, and then try to train a and then try to train a student diffusion model. Um, uh, so and the student model is then trained to get the same results as the teacher model. The optimization function the optimization function is constructed so that the images generated are approximately the same. So that's the optimization function, and what that allows it to do is the student model is also conditioned on being able to do that with lesser number of denoising steps. So what they do in this paper is you train a student model from that pure diffusion model, which is and now the student model has the um, has its objective as to get the same results but in lesser number of steps, and that seems to work out really well because um, yeah, just because it's rather easy to do this, and it has also worked really well for connets earlier. It's still a bit tricky to formally understand how this works, and and they do have some nice reading on that in the earlier paper. This one, you should especially read the supplementary of this. Really interesting and well explained, I guess. uh but yeah, that's like a very rough overview of what progressive distillation is doing. And yeah, maybe now that we are past the standard background, maybe you can just see the method. And this seems a bit dense. This would be nice for a paper reading, but I guess not a discussion. But let's see how we do that. So first they have some figures and then some table, and then they have this on in-step deterministic and stochastic sampling. This one actually looks really close to what DDIMs do. Okay, wait, let's see that. Okay. So that's about their method section. So I guess let's go through their method section. And this is they discuss their approach. Okay, I get that. So they have a single distilled model conditioned on the guidance strength. They can capture a wide range of classifier-free guidance levels, allowing for the trade-offs between sample quality and diversity efficiently. I guess that's nice to integrate in it because like one of the main things with I don't know if you remember, but one of the main things at least with why classifier-free diffusion guidance was introduced was at least like before classifier-free diffusion guidance, what we used to do was um, eh, to make it conditioned on some kind of classifier, we would have uh, we would essentially have this adversarial something feeling like injecting adversarial examples, and then the model just becomes accustomed to not taking into account those adversarial examples, and and that wasn't really a really nice way to approach this. If you think about it, what the model is doing in the backhand is intuitively the model is learning that I have these adversarial examples, but I'll not take them into account. That's what the model is doing in the training process. And that's what diffusion models used to do for a long, long time. Uh, so classifier free diffusion guidance really helps solve that problem. Uh, but, but there's also the trade-off of sample quality and diversity because yeah, because if you just optimize for sample quality, you lose the ability to generate the kind of images pure diffusion models used to generate. That is, from pure noise, you can get literally anything at all. You have no control of what the diffusion generates. So you get the diversity aspect really well, actually, in those cases. Yeah, no need to.
What's the difference between bottom line five something percent?
Yes. So I guess maybe for that, if you just recall like the standard diffusion diagram, uh, 3DPM figure. So this is also my love with figures because whenever I write papers, I think it's really hard for me to make figures. I have spent 16 hours on making one figure. So I like when paper authors work on figures. Probably just way too biased, but if you remember like the standard diffusion diagram or the standard DDPM diagram, what they do is you have this noisy image, you put some noise on it, and now when you are at this stage, you have your unit denoise, try to denoise this image, and that generates some entirely new image. So if you increase the sampling steps, you are asking the unit to denoise the image more, or essentially just passing a relatively more noisy image into the unit once again, and the unit then tries to denoise it once again. So just like more the number of denoising steps. Usually it is better. There's also some scaling loss for this, but usually it improves performance. So then in their method, they say they have this whole text on stage one distillation, which I don't feel. Uh yeah. So but yeah, so like first for the difference, so I mainly kind of picked up that they were using latent diffusion models because in the abstract they say that they also do experiments on lion and ImageNet 256, and I'm pretty sure they don't have the money to do pixel scale experiments on those. But what essentially pixel scale means in a very intuitive way, and anyone like feel free to pitch on. This is just a discussion. But what pixel scale models mean is just the standard thing. You do the diffusion, you train a diffusion model directly on pixels of images. So you have like all these images and the pixels, and you directly pass this in and train the diffusion model. uh, and that's just like the standard approach. People do that since very long. uh, and there was so around the similar time, when we were thinking of or, when the community was thinking of latent diffusion models, there was a lot of talk about feature vectors and how you could optimize stuff on the embedding space. So people were even trying to do this with VITs. So around the similar time, people thought, oh well, what if you do this with diffusion models? And then what you do is you now train the diffusion model on the so let's say you have all of these images or multiple images, and and then you try to train a diffusion model on the autoencoder feature space for all of these images. So you can draw like a nice parallel for this between like dataset diffusion. So what you do with dataset diffusion, um, so what you do with dataset diffusion is you have this huge dataset. I actually have a nice figure. So you can actually draw a really nice parallel to this, and I guess that just makes sense. So uh not okay. So there was this figure. Yeah. So so what I was trying to show in this figure was this is just what dataset distillation or compression techniques for dataset mean. And what you try to do is you have this a huge amount of dataset, and then you try to find out in the feature space or in the dataset space itself, usually in the feature space, you try to convert this into a smaller dataset with which if you learn you get approximately the approximately the same results. That's not formal at all, but that's just what yeah, that's just what dataset distillation does. And this is especially draws a nice parallel between pixel and latent wise, because what you do with the latent with latent diffusion models, and that's also how image and dolly everything stable diffusion is trained. So what you do is you have all of these images, and then you convert them into this latent space, and and then you can train on it. So the latent space is much smaller than the data set itself, which is why you can even do experiments with diffusion on Lion or ImageNet 256. uh, I guess with standard diffusion you are due to just like current hardware, you are limited to ImageNet 64 cross 64. So if you do it this way, you can generate like a lot more high high resolution images, work on even larger data sets, and yeah. So then they have this whole thing about stage one distillation, stage two distillation. Maybe we can go over that. I don't want to read all of it, but they have this learnable parameter eta one. Oh, okay. Well, so uh, we introduce a student model x eta one. This is so this, if you want to draw a parallel to standard diffusion models, it's uh, x theta hat, and that is your denoising part. And for the student model, they say it's x theta 1 hat. And they have this learnable parameter eta 1. Okay, so just like standard diffusion models, when you say x theta hat, this is a lot of parameters. This is parameters for all of the diffusion model. So eta 1 is like a set of parameters. uh, they say a learnable parameter. This is a set of parameters, just because, yeah, this is a standard diffusion. So okay, so now we have this model That's our student model. And what they do is you have your teacher model, and the teacher model, at least right now, should just by knowing about distillation should uh, just be a pre-trained diffusion model. So this will be, let's say, HD or something. So this is your pre-trained diffusion model, and this becomes your teacher model. And then they are now describing their student model. So what they say is, this is your student model, and it can either be a continuous time model or a discrete time model, depending on whether the teacher model is discrete or continuous. And right now they assume that both of them are continuous. Okay, yeah. Changing this for discrete shouldn't be so hard, I guess. At least like in the distillation perspective. But okay, so right now both of these are continuous models, and what they try to do is, so they say a key functionality of classifier free guidance is its ability to trade off between sample quality and diversity, which is controlled by a guidance strength. So this is usually, at least in the classifier free guidance paper, this was W. Uh, and so this is telling us how much guidance we want. And then they just explain that W is valuable. Yeah, it's valuable. And thus we would want our distill model to maintain this property. Okay, so all of this paragraph can be dumbed down to W is a hyperparameter. That's simple explanation of all of this. Okay, I get it. Oh, but you can give it a range of guidance strengths. Oh, okay. So then you have a range of it, and then you would sample across this range. Okay, yeah, that makes sense. So it's still a hyperparameter, and then they say you optimize the student model using the following objective. I think like one part I'm still a bit fuzzy on is, what do you start the student model with? Because at least like connets, because at least like distilling connets, it's very important on what you start the student model with. And I'm just seeing if they also have an algorithm that's in the supplementary. Let's probably take a look at that. Uh, that should be easier to understand. And before, I guess, going to the next part, it's also might be might be nice to also take a look at what the student model is starting off with. So do they have the supplementary in the archive version? I mean, I'm on the archive version as well, but I guess one. Oh, yeah, they do. So then they say algorithm one. Yeah, this is the one. So stage one distillation. Uh, okay, well, I get all of this. And okay. So what they say is, they have the student model, and they also initialize the student model with the same parameters as the conditional model. So this is already an initialized model, and this takes on the same parameters as our conditional model over here. Okay, so now we have our teacher model, our student model. So, and we know what both of them are starting out at. So let's, I guess, take on the next part of it. So so they have this objective function, and so this expectation, if we take a look at this, so the guidance strength is taken from PW. Okay, so PW is just a uniform between WMin and WMax, which was the set of guidance strengths we want. The time step is sampled from 0 to is uniformly sampled from 0 to 1. Okay, and X is sampled from a data distribution, or more accurately, what we think is our data distribution. And what they say is, so what they say is you have the x eta 1. This is the student model you are trying to learn. And then you have the x theta. So this is the pre-trained conditional model you have. And so what you want, so what seems that they are trying to do with this objective function is, so you are trying to you're just trying to optimize this difference. And what that means is, and they also take an L2 now, but okay, yeah. Well, anyways, so I guess what that just means is, you want to train the student model to produce approximately similar stuff as what the teacher model does. So the student model is now training, and the teacher model produces some output. The student model is trying to replicate this output. So so the objective function, at least for the student model, is it needs to try and replicate this output. Okay, that seems nice. And note that here our distilled model is also conditioned on the context C text prompt, which is dropped for simplicity. Okay, wait, but that's actually rather simple to understand, because you just have like this conditioning parameter in the training of this student model. So you have that conditioning parameter C. This could be some text, or this could be something like Dream Booth, where the conditioning parameter is heavily changed. And yeah, this could, I guess, be anything. Um, by the way, like when I meant Dream Booth, I meant like the rare property token, rare token finder in Dream Booth, and not like the fine tuning approach. Sorry, wait. Yeah, so this conditioning parameter could be anything, at least in the training. And then they say to incorporate the guidance weight, we introduce a W conditioned model where W is fed as an input to the student model. Okay, yeah, that also makes sense, because we want to be able to. So even after we are training the student model, we want to have the ability to contrast between how much does this depend on guidance. So I guess that makes a lot of sense. And they incorporate this into the diffusion model backbone, similar to how the time step was incorporated. Yeah. So these are just popular papers. So let's see what the paper 10 is. So the 33 one, which we just saw, was about progressive distillation, and they say 10. So that's this. Oh, variational diffusion models. Okay. So they also incorporate the W parameter, very similar to variational diffusion models or the progressive distillation. And maybe we can find that somewhere. Oh, yeah. They do have that described over here. Maybe you can come to that later. Okay. The part about like doing Fourier embeddings to W. Okay. So that makes sense. And yeah, I guess this part is just a bit about how they initialize and what architecture this is. So they say this is all just a unit, fully convolution. And yeah, so what the student model is trying to do is try to produce the same outputs at stable diffusion. So just for this example, I took stable diffusion, but like whatever the teacher model is, I guess. And then they say something about stage 2 distillation. So in the second stage, we consider a discrete time step scenario and progressively distill the learned model from the first stage. Oh, what's happened? Into a fewer step model. So I guess like this is the main part, because this is the part where you try to incorporate fewer or you try to want to be able to do that in fewer number of steps. So I guess that's the main part of this. And here they introduce another diffusion model. Okay. So this one's called X eta 2. So this is our another diffusion model. And yeah, so now we already have this one which is called x eta 1 hat, this which is called x theta hat, just your standard diffusion. So now we want a new model that says x eta 2 hat. So let's see what this does. And this tries to train a fewer step student model by halving the number of sampling steps each time, letting n denote the number of sampling steps. Well, okay. So they have this sampling steps uh, from t by n to t minus 0.5 by n, and from t minus 0.5 by n to t minus 1 by n. Okay. I see. I think this makes it really interesting, and the parallel to DDIM is also very it's also very apparent right now. But apparently what they're trying to do is you try to train this model, and this model is trying to get the same output again. But what this x eta 2 model does is it doesn't have the same number of sampling steps each time. So you do this training step once, and let's say this is the number of sampling steps, and then you do the training step again, but you do it with what do they say here, t minus 0.5 by n. So you do it with t minus 0.5 by n sampling steps, and then you keep on reducing this, and the objective function still remains the same. That is, you want to be able to generate the same outputs as the ones we generated earlier. So I guess that's that. So I guess that makes x eta 2 low. So the objective of x eta 2 now is to generate the same images but in lesser number of sampling steps, and I guess that's the main step. So what they say is, so once we do this for a single run, which is probably, I guess, getting down to a single step, what you then try to do is use the n-step student model as the new teacher, repeat the same process, and distill the teacher model into an n by 2 step student model. Okay. So I think what they are trying to do is, once you have this x eta 2 model, so x eta 2 model can now do it with t by 2 step number of steps. So then this becomes a new teacher model. So then you start writing x eta 2 hat as x theta hat, and then you do the whole process once again, the stage 1, stage 2, all of it, and then you get a model that does it with t by 4 sampling steps, and so on. Yeah, I see. Yeah, that sounds workable. And I guess, like, so and then they also have this section on n-step deterministic and stochastic sampling. So what they say over here is, we can perform sampling via the DDIM update rule. So we were just talking about the DDIM update rule, and we note that the given distilled model x eta 2, this sampling procedure is deterministic. So we apply one deterministic sampling steps with 2 times the original step length. Okay. So this also, so I guess, like, this is one of the real main contributions of the paper, because this is some really nice reparameterization from what they described. And what they are trying to do is, so this is how they are making the sampling steps shorter each time. And I think this is the real contribution of this paper, just thinking about how you reparameterize this. It would be nice to see how they thought of this update rule. So we apply one deterministic sampling steps at 2 times the original step length, and the same as an n by 2 deterministic sampler. Okay. So if we try to see this, what they are trying to do is, just have this denoising step be twice the size, and then have this stochastic sampling part, add some more noise to it, and what that just allows the model to do is okay. So and what that just allows the model to do is add some more variations to it and generate more diverse images. So that actually makes a lot of sense because so after this denoising step, the model again has the ability to do uh, to do a denoising on the newly added noise, and that allows you to also get some variety on it and also allows you to halve the number of sampling steps. So so that's also what they describe over here. So that's also what they describe in these. So that makes a lot of sense. Yeah. So so I guess that's about the method, and that did seem to be rather interesting, especially at least to me it seemed rather interesting how they try to progressively get models do the same stuff in a single step. Yeah, that's really interesting. And they also have some experiments where they sorry. Yeah, so yeah,
Then, then, those course,
yeah,
now down to the shore. This thing is up for the if I think that's really when my
yeah. So so I do agree with that, and there might also be some other really nice update rules out there. But like one of the things I was just thinking is so first time when I saw this update rule, so one of the things that I thought of was I was actually reminded of the DDIM uh the DDIM update rule. So if we just see this, so DDIM's actually had a really similar update rule, and and that makes and to me it sounded like a nice update over it. And once they explain once they show these update rules, it's also a bit like thinking you're applying DDIMs for you're trying to do DDIM stuff for like training one of the student models. So so at least to me that motivation was uh, at least to me that motivation was pretty solid. Yeah. But I completely agree. There could be like some really nice other update.
guy that so this guy, there's another these two guys, okay? How do you say,
Yeah.
and then I have a question for you, which is for a long time. The presentation, I want your opinion. Is it possible that the something said are a very more probing phase. What's the question? What are we doing? Before we
Yeah. So
I can do, if I have enough computer time, I can do thousands of.
so there's also yeah, I do agree with that, but there's also this no, but there's also but there's also a really interesting scaling laws about. So there's also uh the part about how much the diffusion model has learned, or more accurately, how much the unit has learned, and at least for like a lot of at least for like stable diffusion image and that kind of stuff, a unit isn't able to learn more than 5 and 2 steps. That is around that is the kind of number of steps that they try to train it on. Uh, Imagen was actually purely diffusion, but uh, so so after like a certain point of the number of sampling steps, they're also unable to just like denoise it any further. So but yeah, I do agree that it might make sense to also see how much do these sampling steps, or what each of these sampling steps affects. I don't think
We're
I've
not talking about. Carol, any noise by saying, denoise instead. Maybe after I do the denoise, maybe we can. With the phone.
yeah yes
It's tricky story.
it's also interesting that how you can so what they have shown is if you try to use these kind of update rules, it works really well with cold transforms. So stuff like, so this is Gaussian noise, but if you do stuff like other cold transforms, let's say let's say what are good cold transforms? Yeah, pretty much like a lot of the other cold transforms like degradation, blurring, masking. Yeah. We are at time, but and not to self-promote, but we also have a new reps in review paper which extends cold diffusion for hot transforms, but not to self-promote. But that's all. But that's all for today.